We now proceed to the next example on page 20. In this example, we are told that Anderson Windows makes windows for use in homes and commercial buildings. The standards for glass thickness call for the glass to have an average of 0.375 inch with a standard deviation equal to 0.050 inch. Suppose that a random sample of n equals 50 windows produces a single mean of 0.392 inches. The first question we'd like to answer is, what is the probability of the sample mean being greater than or equal to 0.392 if the windows meet the standards? This condition, if the windows meets the standards, what does it mean? Remember, the standards for glass thickness should be that the average, the mean, should be equal to the mean. Let's write this clearly. The mean should be equal to 0.375 and the standard deviation should be equal to 0.050 inches. That is what the standards means. So that means in the population, in the general population of all the glass thickness, these are the specs or standards required. Given that these standards are met, or if those standards hold, what is this probability? What we'll quickly notice here is that we were not told that the glass thicknesses follow a normal distribution. Well, that means the distribution of the parent population is not known. What would interest us is the sample size, though. The sample size, which is n equals 50, is greater than 30, which indicates that we have a large sample. Since we have a large sample, we can use the central limit theorem, which guarantees that we are free to use the normal distribution to approximate the sampling distribution of x bar, and we just need to find the mean of x bar, which is right here in the middle, and that will be exactly equal to 0.375, but the standard error of x bar will be the standard deviation divided by the square root of n. This will be 0.050 divided by the square root of 50. And this will be equal to 0.00707. So now that we have the sampling distribution of x bar, we can now focus on, we now have the tools to find the probability of x bar greater than or equal to 0.392. My first step will be to locate 0.392. That should be to the right of 0.375. So 392 right here. And we're interested in the probability that x bar is greater than 0.392. So we have that right here. And our interest then will be to use our normal distribution calculator to find the size of this probability. So on the screen, I have captured the parameters of the distribution. So all I need to do next, going back to my workspace, I am going to indicate that I'm interested in the probability area above 0.392. So going back, I'm going to specify above 0.392 and hit the enter button. And I have the required probability, which is 0.0081. So my answer here is 0.0081. What does this mean? This means that if I multiply this, for example, by 100%, I'm going to get 0.81%. So there is a 0.81% chance that the sample mean will be greater than 0.392 or even equal to that value. That represents a very, 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 very small probability that we will observe this value. Okay, having interpreted that value, let's see what it means in the context of real-life problem solving. Question B. Based on your answer to part A, what would you conclude about the population of windows? Is it still meeting the set standards? Remember, the set standards is that the mean should be 0.375 in inches and with a standard deviation of 0.050 inches. Well, if the windows are meeting these standards, the probability that the sample mean will be this value, 0.392 inch, is 0.81%, which is extremely low, not even up to 1%. So, if we are observing that value, 0.392, when we drew this random sample, it is an indicator that we're observing a number or a sample mean that is highly unlikely, which may be telling us that these standards are no longer being observed, or these standards or assumption may no longer hold true. It may also be telling us that the sample we have drawn for this sampling process may not be a truly random sample that is representative of the population of the thickness of glasses. To be clear, there are two possibilities here. The very first one is that if the population of window thicknesses are still meeting the set standards of mean equals 0.375 inches and standard deviation of 0.050 inches, what we observed in the calculation in part A is that the probability of observing a sample mean of 0.392 is extremely low at 0.81%. What that means is that we're observing something that is highly unlikely. If it is highly unlikely, it might be telling us that this population assumption, specifications, or the specifications in the assumption might no longer be holding true. And to emphasize that, we have written it down. This may indicate that the assumptions in the population that the mean is 0.375 and the standard deviation is 0.050 may not be true any longer. Another possibility too is that the sample that has been chosen for this exercise may not be a truly random sample that represents the population of the glass thickness windows. Let's write that down. So, as mentioned earlier, it may also be that the sample drawn in this sampling exercise may not be a truly random and representative sample drawn from the entire population of numbers that represents the window thicknesses. The fact that we're observing a very, very highly unlikely incident or event here points to this possibility too. So with that said, we proceed to page 21. In this example, we're told that mileage ratings for cars and trucks generally come with a qualifier stating actual mileage will depend on driving conditions and habits. Ford states that the EcoBoost F-150 3.5-liter V6 will average 20 miles per gallon with combined town and country driving. We're to assume that the mean stated by Ford is the actual average. So if that is the population average, that will mean that we're looking at 20 miles. That's what that means. With a stand, and the distribution has a standard deviation of 3. Now, based on the given parameters, question A, given the above mean and standard deviation, what is the probability that 100 drivers will average more than 19.2 miles per gallon? In other words, we would like to find the probability that for a given sample size n equals 100, the average x bar for that sample will be more than 19.2. This is the question we would like to find. Since the probability is related to the sample mean, we will need to get the sampling distribution of X bar. And that will necessitate finding the mean of X bar, which of course will be equal to exactly the population mean of 20, and the standard error will be sigma divided by the square root of n, that will be 3 divided by the square root of 100, which is 0.3. Now that we have the parameters of the sampling distribution, namely the mean of all the sample means and the standard error of the sample means, we can then go back to find or to locate 19.2 and say that in this region, we're interested in the area above 19.2. And we can take that to our normal distribution calculator. So I'm going to key in the parameters in the calculator. First of all, my mean is 20 and my standard deviation is 0.3, and I'm interested, based on this picture, in the area above 19.2. So I'm going to click on above 19.2 and hit the enter button. So I have 0.9962. So this is equal to 0.9962. Done. Then, for question B, we are to suppose that 1,000 drivers were randomly selected, which means the sample size has now been adjusted to 1,000. We would like to find the probability. What is the probability that the average obtained by these drivers will exceed 19.2 miles per gallon? So, under these conditions, we want the probability, capital P, that average of the sample will exceed 19.2. That means will be greater than 19.2. That will be, we'll go through a similar process as we did earlier in part A, only that the sample size has changed. So let's see what changes to. The mean of X bar will always still be the mean. However, the standard error of X bar will be standard deviation divided by the square root of n. That will be 3 divided by the square root of, my new n is 1,000, no longer 100. So what would this be? This is equal to 0.095. And I can then proceed to locate 19.2 right here. And this indicates that I'm interested in the area greater than or above 19.2. And based on that, I need to reset the standard deviation. So 20 and this value. So I'm going to go back here, reset the standard deviation to 0.095. And I am still interested in above 19.2, and I can see that the probability is 1, which represents the probability of certainty. So this is approximately equal to 1. That is a final answer there. With that said, we complete that question on page 21, and we proceed to page 22. This question says that suppose a market research analyst for a cell phone company conducts a study of their customers who exceed the time allowance allowed on their basic cell phone contract. The analyst finds that for those people who exceed the time included in their base contract, the excess time used follows an exponential distribution. All you need to note there is that this is not a normal distribution with a mean of 22 minutes. So the parent population is not normal and is given another name, namely the exponential distribution, but in particular, its mean is 22. And we are also to suppose that the standard deviation is also 22. Consider a random sample of 80 customers, so n equals 80, who exceed the time allowance included in the base cell phone contract. Let X be the excess time used by one individual cell phone customer who exceeds his or contracted time allowance. Thus, X bar here represents the mean excess time included in the base contract, base cell phone contract. That is what X bar will be. It will be the sample mean of these 80 customers, the sample mean of all the excess times they used. Now, based on this, our goal is to note these population characteristics and answer question A. We are to find the probability that the mean excess time used by these 80 customers in the sample, so it's a mean pertaining to the sample, X bar, is longer than 20 minutes. Longer than 20 minutes means greater than 20 minutes. This is a probability associated with the sample mean. And so we need to draw this because the sample size is 80, it is greater than 30, so we're allowed to use the normal approximation, and the mean for my X bar is going to be exactly equal to the general population mean of 22, and the standard error will be sigma divided by the square root of n. That will be 22 divided by the square root of 80. This will be equal to 2.4597. Okay, then with that, I am ready to locate the number 20. This is the number 20, and I would like the area above 20, to the right of 20. So I'm going to take the parameters to the normal distribution calculator. So right here on your screen, you can see the mean and the standard deviation already keyed in. I'm now going to go back. With regard to the number 20, I am interested in the probability area above 20. So I'm going to set up that. So I want above and 20 and hit the enter button. And I have the required probability of 0.7919. So this is equal to 0.7919. Then question B, we are to find the 95th percentile for the mean excess time used. Round to the nearest whole number. So this is the derived distribution. The derived distribution is such that the mean of all the sample means is 22, and the standard error is 2.4597 for the population of all the sample means. So as far as this question goes, we are to find the 95th percentile, which means I have to find a number here, whose name is the 95th percentile. That is just the name, but its value is my final answer. It is the 95th percentile because 95% of the mean excess time lies below it. So I already have my area here. I would just like to find the value. From what we learned under normal distribution, since we already have the probability, we only want the value, we're working in reverse. So that means I want the inverse normal distribution calculator. So let me remind you, in this case, we will need to open the inverse normal distribution. So I'm going to right-click this and open this in a new tab. So I have the inverse normal distribution. It's asking me for the area. It is 0.95. What is the mean of this distribution? The mean of this distribution is 22, and the standard deviation is 2.4597. So I'm going to key that in. So I have 22 and 2.4597. Again, 2.4597 comes from the parameters of the distribution. And I'm interested, this area, I have to indicate that it is an area below. So let's go back. I'm interested in below, and that will give me 26.046. So I have my answer. That is the value, 26.046. Again, just to check, 26.046, approximately 26 minutes. Or what is it measured in? Yes, the times are measured in minutes. So this will be approximately 26 minutes. So approximately 95% of all the excess time used, of all the mean excess time used, would lie below or equal to 26 minutes.